Welcome again to this evening's technical joint branch meeting, Southern Joint Branch technical meeting. I'll get it right for the third time, looking at the effects of alternative fuels on a 68-metre super yacht. So welcome to those of you joining us in Solent, and welcome to those of you joining us as well online. Vittorio, over to you.
So, sorry, I repeat once again, it's technical issues, fine. So this is a paper produced by myself and by Harris Maidment, who is a former student of Solent University. He developed part of the paper in as part of his dissertation for the master in super yacht design. So we analyzed the effect of different types of fuel on a super yacht, and we took into account several factors that we are going to develop during the slides. And we started with the idea of the targets that IMO set for the reduction of carbon emission, carbon dioxide emission, and green gas emission for 2 different days, 2030 and 2050. And we effectively thought, what is going to happen if now we get rid of traditional diesel and we move into some carbon neutral fuels? Of course, we immediately reach the target set by IMO in terms of emission, in terms of reduction. But what is going to really happen to the boat ship in terms of refueling, storage, propulsion and energy generation, and what are the requirements that we need to comply with the new fuels in terms of rules? The starting point for us was to take the amount of energy that a 68-meter super yacht is able to bring and to convert it into an equivalent amount of energy produced by an alternative fuel, neglecting the efficiency of machinery like internal combustion engine or fuel cells. So it's just a swap from energy to energy. These are some limitation, of course, because fuel cells are more efficient compared to internal combustion engines, but either in the similar way, internal combustion engine which can run on methanol or on ammonia have a different efficiency. So to make it simple, it's just swap fuel by energy without assessing too much the efficiency of the different systems. Next. So the starting point is a kind of a modern super yacht, an explorer yacht, 68 meters, able to cross the Atlantic. So this was developed as part of the course in super yacht design here at Solent. Really, we are interested in the main characteristic of this yacht in terms of engine requirement. So 2 engines of 1,678 kilowatts, and the amount of fuel able to cross the Atlantic. So with an autonomy of about 4,000 miles. So with the amount of fuel we need, we need to design on board a storage of 109,000 liters. So that's basically our starting point. And from this amount of fuel, we've worked with equivalent fuel to see what is happening if we need to swap tomorrow to different fuels. In order to assess how good some alternative fuels can be, we took part of this part of a work developed by DNV. This is an assessment for conventional diesel as benchmark, as comparison against biodiesel, renewable methanol, renewable hydrogen, and renewable ammonia. The DNVGL develops a map where they grade the fuel from a scale from 1 to 5, where 1 is really bad and 5 is really good. And they rated the fuel according to a series of parameters. Depending on the parameters you take into consideration, some fuels can be more competitive compared to others. So if we think about 5 primary criteria, which are energy density, flammability, toxicity, local emission, and greenhouse emission, you can see that if you draw the average, well, we can't see because it's a little bit down, but basically the biodiesel becomes green, and that's the most efficient among the 5 fuels. While if we consider all the criteria, we can see that's the first one to come into the in our rating is diesel. So the assessment of the fuel basically needs to take into account different factors, not only the greenhouse emission, but also other factors which sometimes are relevant for the owner, like, for example, capital cost, energy cost, and for the operativity of the ship, bunker availability, and technological maturity. To swap from energy to energy, we start with conventional diesel, 35 megajoule liter in terms of energy production for liter of fuel. We require 109 cubic meters for an equivalent weight of 91 tons. So that's our starting point. If we swap to different fuels, let's see what is going to happen. Start from the right, biodiesel, a slightly lower energy density. That's imply a larger volume, 111 cubic meters, and a slightly bigger mass, 103 tons. So roughly the same amount of volume and weight. Methanol has less energy density. Therefore, you need to increase the volume to 240 cubic meter and a mass of about 200 tons. Ammonia is a gas at room temperature. So for ammonia, it's very likely that the fuel will be compressed, and at 20 degrees at 9 bars, it becomes liquid. So it's relatively simple as process. By compressing it into a liquid, equivalent energy talking, we need 210 cubic meters for a mass of 128 tons. For hydrogen, everything is a little bit more complex because hydrogen is a gas which has basically an energy density of 0.011 megajoule per liter. So at room temperature is basically not storable because it doesn't have any energy for unit of volume. So the method to store hydrogen is either compressing it or to cool it down until it's not going into liquid form. And there is also the possibility to cool it down and then to compress it. Next, please. Here we are. So hydrogen is normally compressed either at 350 or 700 bar. And you have a density of 2.5 or 5 megajoule per liter. That's correspond to a volume of 1,500 tons or 3,000 tons and a mass of 774 tons or 979 tons. It has to be noted here that the mass includes, in the case of hydrogen, the storage. Hydrogen for the high compression pressure can be stored in the ship as in tanks built by the ship, but needs to be stored in appropriate bottles, appropriate containers. So the weight of the fuel in this case takes also in consideration the weight of the containers. We can push. So if we have a look at the graph on the right, we're working now with compressed hydrogen in the area denominated with number 2. We can work also by cooling hydrogen down and so bring it into liquid form. That would happen at a temperature of about minus 250 degrees Celsius, so quite a lot. If we use cryogenic hydrogen, then we work with an energy density of 8 megajoule liter. That is equivalent to roughly 1,000 cubic meters as storage on board and a mass of 1,000 tons, again, including bottles. We can also compress hydrogen in liquid form. So we have a cryogenic compression storage. We increase again the energy density to 15 megajoule liter. Volume reduces to 500 cubic meters and a mass of about 500 tons. So that's basically a table which summarizes all the data. It's quite interesting to see how much volume, oops, okay, how much volume, how much more volume some fuels are going to take compared to traditional diesel. The mass might not be too much of a problem, although the mass, if you compare diesel with hydrogen, we go up to 10 times in terms of only fuel, of course. But the volume that we need on board is much, much bigger. We then had a look at refueling options, because apart from storage, we need to have this fuel on board. With hydrogen, there are some options depending on the type of storage that we have on board. You can think about swapping the whole tank. So take the empty bottles, replace with some new bottles. That could be kind of an easy way. There are other options to have on board compression rooms. So you take on board hydrogen in a gas state, and then either you recompress to store it at 300 or 700 bars, or you need to compress and cool it down to reach the cryogenic temperature. Both of solution, of course, imply much more volume on board for the storage and much more energy to compress the hydrogen and store it. Refueling for biodiesel is conventional. It's liquid, so it's relatively simple, as it is for methanol. For ammonia, it's very likely that because the gas is going to be pumped on board using gas form and then compressed on board. Remember, the compression is only 9 bars, so it's not too much of a problem, and then recompressed on board to be stored in liquid form. In terms of impacts on the propulsion system and in terms of, widely speaking, general energy generation, if you take biodiesel and you burn it straight away into combustion engines, you have a 10% power reduction, about just because of the slightly lower energy density that that biodiesel have compared to traditional diesel. If we use methanol, methanol can be used both in internal combustion engines and in fuel cells. Internal combustion engines exist on the market. Dual fuel engines are available. They can increase in some condition the efficiency. There are attempts to do research in methanol fuel cells. At the moment, they're really not ready to be tested on the market. Ammonia can be used in combustion engines. Again, industry is already producing engines running on ammonia. They of course had to change the fuel ratio due to different ratio between ammonia and air, and due to technology related to the flame speed into the combustion chamber. There are also some study done on ammonia in terms of fuel cells too, but again, as with the methanol, the technology is a little bit too early and there are no commercial application. If we have a look at hydrogen, of course, hydrogen is widely used in terms of fuel cells. Is the best way to use hydrogen as fuel production. That of course produce electricity, doesn't produce mechanical energy. So that can be a viable solution if you couple your generators with an electric motor, or if you want to use hydrogen fuel cells as diesel in replacement of diesel generator on boards. You can use hydrogen in internal combustion engine that has a ideally there's a stoichiometric ratio of 34:1, but that ratio is a little bit too high and the engine tends to suffer of pre-ignition, so you need to use a lower ratio, 68:1. That implies that you reduce the maximum power about 50%, And to overtake this problem, you need to start to use turbo compression, boosting, and direct injection system, all the technology to try to improve the energy efficiency without having the negative aspect of reignition. So in terms of internal combustion engine, we have the full compatibility of the 4 different fuels with different level of complication. Biodiesel, literally minor modification. Literally the rubber needs to be changed and some other bits and pieces, but very, very minimal modification. For methanol and ammonia and hydrogen, we need to bring into the engine some several modification, which part of which the industry has already overcome. In fact, we have hybrid, other hybrid engines with dual fuel engines with methanol and ammonia run engines. Because some engines running on different fuels are running at high temperature, a little bit like modern diesel is doing, there is still a risk of production of NOx during the combustion process. In terms of fuel cells, hydrogen, no problem at all. Methanol, biodiesel, and ammonia, that technology is very, very early, so there is literally no commercial development at the moment. The impact of fuel in terms of regulation. Biodiesel, no modification at all, swap one for the other, off we go. Methanol starts to become a little bit complicated. Tanks and pipes needs to be 800 millimeter from the ship side. There must be around the tanks as A60 cofferdam, 600 millimeter space, nitrogen purging system, and piping with double walls and gas tight. So a lot of complication in the development of the system on board to make sure to comply with the rules. Ammonia, Bureau Veritas has issued a tentative rule, which basically has the same limitation of methanol. They have the same problem, although ammonia is much more dangerous in terms as for the human body, basically. So they are working on being careful with the monitoring system for ammonia. Hydrogen has similar problem with methanol too. 1.5 times 2.5 meter airlock, 900 millimeter cofferdam surrounding. The compressor storage can only be stored on the deck like LNG. For fuel cells, some rules provide a minimum boundaries against the fuel cells needs to be gas tight, access from open deck or airlock, and 600 millimeter A60 cofferdam, effectively to prevent explosion and to prevent contamination of pockets of hydrogen, which can lead easily to explosion due to the nature of the fuel. So biodiesel has no modification in terms of ship design. Again, swap fuel and off you go. Ammonia and methanol requires bigger volumes because of the cofferdam, and the design of the fuel system is much more complex. Hydrogen requires more volume taken by the cofferdam and by the airlocks. The compressor storage can cause stability problem, and we'll see it in a couple of slides, because it needs to be stored outside. That's the summary of the table that I showed you before with the impact analysis in terms of mass and volume. So based on diesel, you can see that the amount of mass that the fuel is going to take is much bigger. In particular, if we start to use hydrogen, mainly due to the weight of the storage that we use. The same happens with if we have a look at the volume, at the mass, which is the the ships on the below 2 rows. The increase of mass is quite significant based on diesel, and again, this is due to the certainly big amount of fuel that we need to bring on board, but again, also for the weight of the storage system that is start to become a little bit of a problem for hydrogen. If we have a look at renewable methanol and renewable ammonia, both of them increase the mass and the volume on board, but not dramatically. So in terms of storage, hydrogen has a lot of problems, while ammonia and methanol have much a less smaller impact compared to the other. The table here summarizes the values of the increment in terms of displacement and final displacement of the ship compared to diesel, and the table on the right does the same, but in terms of volumes. So the increase in terms of percentage are quite big. These volume don't take into account any cofferdam. So it's just the storage for the fuel. Also consider that if you store the fuel in small bottles, like hydrogen, the volume that you need to use is even much bigger because you need to store one bottle close to another. So it's much bigger. The effect of different fuels on stability. Let's start from the worst case scenario, green, hydrogen. Compressed hydrogen needs to be stored on the deck. Take that mass, about 1,000 kilos on the deck, and the boat becomes immediately unstable. Compared to a traditional stability assessment. So that creates a lot of trouble, of course, because the storage outside required a complete redesign of the boat, a rethinking. You can't just take that mass and put it on the first free deck. Similarly happens with cryocompressed hydrogen, which is the yellow line, which shows an instability at 0 degrees. On the contrary, the other renewable fuel, so it's ammonia, it's methanol, and it's cryogenic hydrogen, which can be stored under the deck. They all show an increase of stability simply because we increase the mass of the fuel below the waterline, so we actually increase the stability. So the effect on these is positive. So we run based on the general layout of the second slide. We rerun a kind of a attempt to redesign the boat very quickly to put hydrogen on the first useful deck. So imagine to remove part of the space toward the transom, possibly, which goes in terms of tender garage, in terms of part of the accommodation. Imagine to redesign that area and just dedicate that area for fuel storage. And can we go to the next one? And that's what is going to happen. So we were able to move the stability from the 70 from the green line to the orange line. So the boat becomes stable, but whether it's passed the rules or not is very much let's just say no way. Yeah, it's very likely it doesn't pass. But it was a kind of an exercise to try to understand a little bit more the impact of the fuel on the stability. So it is problematic. So draw a line and start to see what we can do in the future. I think the one of the best way to move a little bit forward, to start to meet the 2030 targets and then moving toward the 2050 targets, to try to blend the fuel. So going slowly toward the transition from using all diesel to using also some kind of renewable fuels. Blend them together it is a possibility. For small ships, hybrid can be a solution. We are studying at Solent some alternatives in European funded project called ISHI, and we are developing some solution for small vessels up to 40 meters using a combination of hydrogen and electric system. So if we redraw a line and we say, okay, biodiesel is promising, we can use it relatively simple without too many impact on the design. Ammonia and methanol are promising-ish. They both imply more complexity and more complexity of the system and more cost due to fact that you're losing part of the cargo. You will need more space on board, but is a possibility, concrete possibility, because industry is developing engines for those two fuels. Hydrogen, in terms of internal combustion engine, is very unsuitable at the moment. It's easier to use ammonia and methanol. It is much more suitable as a fuel if we use it as power generation in fuel cells. Clearly, the analysis that I presented shows that if you need to apply modern technology on a super yacht, you need to rethink the full yacht. The weight increases, the volumes are going to change, so the vessel needs to be redesigned, taking into consideration these new fuels. And if you want to use hydrogen due to the volume of the fuel, that's, I think, requires a complete redesign of the vessel itself. Last but not least, the industry will move according to the availability of the fuel. Now, if you build tomorrow any kind of vessel, any kind of ship running on methanol, running on ammonia, running on hydrogen, and you want to refill it, the problem is that there is no fuel available at the moment. So if you think about that, industry is kind of ready with the technology, but doesn't know where to move because there is no way to refuel the ships tomorrow. And that is a big problem because that is a kind of a limiting factor in the development of our industry toward a greener transition. Any questions?
Sorry, how will superyachts that are potentially fiberglass cope with ultra low temperatures? Because hydrogen cryogenically is -250. You know, so then you're going to have to think about specialized pipelines that are going to withstand low temperatures. I mean, it's bad enough loading a normal gas tanker.
No, I completely agree with you.
Yeah. And then you've got the crew. I mean, at the moment, where the cruise ships are going through changing to LPG, the crew are all having to come on gas tanker safety training courses, so they learn how to handle new fuel.
The idea that we had was not to assess, let's say, in a way, the feasibility, but to assess what was going to happen if we were going to swap technology. Of course, our work is in a way, and I made it clear since the beginning, limited by swapping fuel for fuel. You are absolutely right. Cryogenic hydrogen at -250 degrees creates a lot of problem. You need to design the ship to make sure that the cohabitation is as it needs to be perfect. You need to spend energy to keep it under temperature.
Well,
So
not necessarily. It's the cool down process for actually taking it on board or whatever, but it's the insulation that's the major problem, because, you know, with LPG hydrogen, you've got to have one tank membrane and then you have to have a secondary membrane depending on the type of tank. If it's a pressurized tank, you know, like the bubble boat gas boats, they have just a drip tray underneath. because it works quite well, but then you have to have the space inerted with nitrogen, which then is, you know,
Yeah, no,
practical.
there are a lot of things that needs to be taken into consideration. It's not simple. Absolutely not. And you pointed out also that there is a problem of people who are working in industry. The rules are moving towards newer fuel, but the training is not moving toward the new fuel. So if tomorrow I'm going to build my ship running on ammonia and I'm gonna have the fuel to refill it, I don't have the crew because I need to train crew to the new fuel, because ammonia in particular is very dangerous. So it's that there is a lot the industry needs to do. Sorry?
It's one of the 4 big nasty gases, 1G containment.
Yeah, absolutely. It's absolutely lethal. It's horrible. Yes, so industry needs to do quite a lot, but we need to do a lot in all the area. We need to do a lot into the design, into the development of systems, into training, into also I think educating people that it's a move that we need to do, and that implies a lot of change. Also, for example, in the infrastructures. Think about refueling hydrogen. Okay, imagine tomorrow I want to build a hydrogen deposit here down in Southampton. How many people would be happy with that? Now they don't know that there are fuel deposits, you know, to bunker ships. But if you tomorrow are going to say, okay, I'm going to put one of the more explosive gas in Southampton to refuel ships, how many people would be happy with that? But is this that's the direction where our industry needs to go? Again, I'm not saying tomorrow we are going to use hydrogen or ammonia or methanol. I honestly don't know. I'm just saying that we need to think about that under multiple points of view. And you're quite right. Training is one of them as technical problem to store this fuel on board.
It's a holistic approach from the industry.
Absolutely, absolutely. 360 degrees.
Before we continue with questions from the room, I'd just like to invite those online. If you have questions, you can just type them into the Q&A chat. We'll read them out and then Victoria will answer them. So please feel free to ask questions. And then I have a question of my own.
Please.
You talked about with some of the fuels, the need to put them on the deck, and also they were very, very heavy. How likely is it that a super yacht owner is going to be willing to sacrifice their jacuzzi for an alternative fuel? Because that's what they're going to have to lose. They're going to have to lose their toys. They're losing their deck area they like to have parties on.
And that's the reason why I said we need to rethink the design. You need to nearly, if you want, particularly if you want to use hydrogen, you need to think about, okay, that's the storage of the fuel I need, and I will build my GA around it.
Yes.
Whether it's going to work or not is a completely different matter. It might not absolutely not work. You know, it's an exercise that you need to do in a way.
That's true, and I think on conventional ships that's easier because the owner can go, you know what, I'm going to try this alternative fuel. But for a yacht,
Absolutely.
it's very much about pleasure. That's pleasure craft.
It is indeed, but you need to put yourself also in the perspective of the owner. Does he want to be the one which creates CO2, or does he want to be the one which is green?
Yes, although if the owner wanted to be green, they wouldn't have a yacht.
Well, it's an industry. It's an industry that works on wealthy people that want to go on a yacht. To be honest with you,
So we just have a quick question, not actually a technical question, but this person has problems joining and wants to know if there'll be a recorded lecture. There will be a recording of this lecture on YouTube, provided you agree.
No problem at all.
Great. At some point next week, it will go up.
Yeah, it's fine.
Just search for Reno and I'm a joint branch on YouTube, and you'll find us.
No, coming anyway to your point, in a cargo vessel, in a commercial vessel, you have much more freedom to play with the GA and with the possible different solution you can have. And as I said before, in our European project initially, we are doing hybrid solutions. And yes, there are some limitations on the GA, but it works. It works relatively simple. while if you have a super yacht, it's much more challenging, and that's what one of the aim of this, you know, this work, to think how much do we need to work as industry to make sure that our super yacht industry is green, and there is a lot to do.
Is there another question from the audience here?
Hi there. Yeah, I was just curious of how you calculated some of your numbers. Did you say that you've assumed the same efficiency for all of the fuel types?
Yes,
And
there's a big assumption, of course. The reason why we did that is because we were trying to understand how we could convert that amount of energy that diesel requires into something related to another fuel, without making the paper too difficult in a way to come to a solution. So if you think about internal combustion engines, they might have the same efficiency. The real problem, they might say, the real problem is with fuel cells, because particularly with hydrogen, the fuel cells have a higher efficiency. Okay, and so that's where hydrogen can start to become a little bit more competitive, because you increase the efficiency, hence you need to decrease the amount of fuel that you store for the same production. Okay, that's one of the limits for sure, absolutely. But that was the easy way to compare the four of them, without too much headache and without too much assumption also for some internal combustion engines, because the data of methanol, of the dual fuel or ammonia engines are not available. Simple as that. Also, another thing that's for some fuel is difficult to assess: how much, imagine hydrogen, how much energy do you need to spend to keep it cryogenic? How much energy you need to spend to repump, to recompress hydrogen? That needs to be taken into account, of course, in the fuel, in the consumption of the ship. So that was really difficult to assess. And so this is why we spoke energy for energy. Brutal, yes, but
I did have a second question as well.
ask the second question then.
So generally, a lot of ships tend to carry more fuel than they're ever likely to use in a single trip.
Very likely so.
Your calculations were based on the existing fuel tanks, or
yeah, the calculation we've done on the super yachts allowed the super yacht to cross the Atlantic. That's normally what a super yacht is designed for. You cross the Atlantic, and then once you arrive on the other side, you refuel. So you bring enough fuel to do 4,000 miles, basically. That was the assessment of the fuel.
We have another question online.
Yeah.
Can you please give your prediction as to what fuel yachts will be using in 2050, bearing in mind the green requirements that are likely at that time?
This challenge is very, very difficult. I was listening last year to one of talk of Ryan Amaris, and I did actually put the same question. It was a guy from Lloyd Register, so you might remember him. It is very difficult. Let's say that at the moment, the biggest problem I see for fuel development is no one is giving a clear indication of what kind of fuel we want to use for our future. And in fact, you can see engine manufacturer working in different directions, because you get methanol engine as ammonia engine, and the owner at the moment don't know what to do, because they don't know which fuel will be developed. And the EU is pushing towards with some directives toward hydrogen, because in a way can be simpler to produce, because you start from hydrogen derived by fossil fuels, although you don't know what to do of the carbon of the gas, and then you try to store it to make a blue hydrogen. And then if you have enough electricity, you may produce electrolysis, and with an excess of energy, of course, you produce electrolysis, you produce green hydrogen. So that's possibly the direction that we might have in Europe, and possibly for small shipping because they have less problem in refueling. For big ships, I think the right move, as industry is indicating, is toward either methanol, either ammonia. And I think between the two, methanol is a little bit less complex than ammonia-ish. I hope it answered. It is a very complex answer, and is more a guess than anything else, to be honest with you.
Well, we haven't asked a follow-up yet, so we do have another question online. Is the industry ready to make a suitable quantity of these alternative fuels?
No. Tanks are empty tomorrow. Absolutely no, absolutely. And even worse, if you think about renewable, because renewable needs to come either by production which has a zero carbon emission, or so from, for example, in the case of ammonia, from a renewable electricity which comes from renewable energies, or in case of methanol, possibly from crops like biodiesel, and we don't have any spare seeds or grain or anything to use to produce fuel. At the moment, we're eating everything. So the simple answer is no, we don't have any fuel. And also the reason why hydrogen can be a little bit more likely to become competitive, because you can break down water and you get hydrogen.
Do you have any more questions in the room?
If you go back to your diesel curves, there's quite a big difference between the biodiesel and the diesel, but I think there's only about 11% difference in the volume. Have I made a mistake?
Diesel and biodiesel are,
Red line and the top line.
yes, the difference in terms of volume was about 2-3%, and the mass was about 10-20 tons, something like this, if I remember well. Yes, if I remember well, that was the difference. Yes. Yeah.
We have a couple of more questions online. The first one is, do you think there's a place for sales as part of a hybrid propulsion mix for making long passages?
Yes and no. They can help in the way of reducing the amount of fuel we burn. They are not alternative propulsion system. So if you think tomorrow using a flattened rotor, that's something similar to a sail, which has been already tested, that could help in the reduction of carbon emission. It doesn't solve the problem. So yeah, yes and no.
About energy efficiency, rather.
Yes, we work. Yeah, yes. Doesn't solve the problem of 2050. It helps to reduce the emission for 2050.
Well, the next question is ethanol discounted as a potential fuel? It isn't often mentioned, but higher energy density and less toxic than methanol.
I honestly don't know. That's the most simple answer. I know LEB is used into fuel the petrol that we buy is a E10 as a certain amount of ethanol, but no, I don't know about application in our industry.
Well, at the moment, there's no more questions online.
Cool.
Oh no, we have just got one in. Biodiesel seems to be the simplest option as a green fuel, but would widespread production of biodiesel put pressure on the cost of producing other crops for food?
Yes, we need to expand the production of crops to produce biodiesel. I do remember Audi, if I remember well, did as an experimental camp somewhere in Germany, where they have a plot of land, produce the crop, produce biodiesel, and use the biodiesel in their engine to see how the technology can be used. So yes, we need to. If we want to use biodiesel, we need to produce it, and it's going to have a huge cost, a huge impact in terms of environmental, because we need to reduce forests to produce more fuel. Yes, they will be renewable, but we know that we need we need a certain amount of nature to grow and to preserve the natural habitat of our planet. So it is easy swapping to biodiesel. The production again is our bottleneck, is our problem.
And I suppose it somewhat defeats the purpose of alternative fuels if we end up having to cut down a load of trees and
Absolutely,
that we would otherwise use to soak up CO2.
absolutely. It's yeah, it's a little bit of a problem. Yes.
There's another question online. Did your space and weight considerations factor the additional equipment required for storage, e.g. refrigeration pumps?
No. No, we didn't take into account any, again, because we, like I was trying to explain before, with the energy density, we didn't take into consideration any additional volume, because it is very difficult to assess, and it could change for different types of fuel, because you might need to have just a pump station to compress, or you can have a multiple stage pump station that takes much more volume, and you need to also to cool down in case of cryogenic. So no, we didn't take into account any additional volume for recompressing the fuel, only for the storage of the fuel itself.
Okay. Any more questions in the room? Standing to silence.
That's fine.
Don't appear to be any more questions online. I think we will call an end to the Q&A.
Fantastic.
Invite Jonathan back to close the lecture.
Okay, thank you very much, Victoria. Very interesting, very obviously very important topic, and one that we'll be grappling with for a long time to come. So we just show our appreciation in a normal way, please. Again, thank you very much for coming. Do appreciate you coming out, and please do keep an eye on the Eventbrite page for the next event coming up soon. Thank you very much, and safe journey home.